35. A kite, 100 feet above the ground, moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of the string has been let out? So let's first draw our picture, which would be, the kite, like this. And we know it is 100 feet above the ground, so that'd be right here. And then it moves horizontally at a speed of 8 feet per second. So this is 8 feet per second. And then we also know that 200 feet of string has been let out. So that's indicating that this part right here, which we'll call H, is 200 feet. So let's take a list of our qualities that we have, which is 100 feet is our y, and then our dx dt, this part right here, the 8 feet per second, and then we also have h, which is 200 feet, but we need to know at what rate is the angle between the string and the horizontal decreasing. So that would be d theta over dt, which is our theta's right there. So that is our unknown. So now we need to figure out an equation. So this is our x, this is our y, but 100 feet will stay constant. So we could use tangent theta, because in the question it's asking for the angle between the string and the horizontal. So that's this part right here, that's the x right here. So we could use tangent, which is opposite over adjacent, which is 100 over x. So now that we have our related rates equation, we can take the derivative of this in respect of time. So our derivative of tangent would be secant squared. And then don't forget we have to have this right here, which is the derivative of theta due to respective time, equals, so right here, to take the derivative, we could also rewrite it as this. So we could use the power rule on that to be much easier. So for the power rule, we know that this goes down, so negative 100 x, and then negative 1 minus 2, which is negative 2, times the derivative of x due to respective time. Yay, now we have that. So now we're trying to solve for the derivative of theta due to respective time. So now all we have to do is divide it by secant squared. So derivative of theta divided by dt over 100 all over secant squared theta. So we could also rewrite this as negative 100 times dx dt over x squared times secant squared. So we could move the x squared down because it is a negative exponent. So if we move it down, it makes it a positive exponent. So now we have the equation for our derivative of theta due to respective time. So now we just have to plug things in that we already know from our list. So negative 100, and we already stated that dx over dt is 8. So, and then now we need to find x squared, which we can do that from using a Pythagorean theorem, which is x squared plus y squared equals h squared. So we know everything except x squared, so we can plug in 100 for our y, and then h is 200. That leaves us with x squared equals 200 squared minus 100 squared, which simplifies to x equals 100 times root 3. So now we know our x, we can put it down here. So 100 times root 3 squared equals, well, not equals, times secant squared. So the way we could find secant squared is, remember our trig identities, which is 1 over cosine squared theta, which would really be, so we know cosine is adjacent over hypotenuse. So, and then we know that would simplify to hypotenuse over adjacent. So hypotenuse over adjacent would be our 200 over our adjacent, which would really be our x. So we found that from right there, which would be 100 times root 3. So now we can put that back in. 200 over 100 root 3 squared. So now all we need to do is simplify. So looking, we have some common terms right here, so these will just cancel out. And now we're left with 100 times 8 over 200 squared. Sorry, I forgot that square. And then that's 800 over 40,000, which is really negative 1 over 50. So now we need our units, which would be radians per second. So therefore our angle is decreasing at a rate of 1 over 50 radians per second. Okay, so realize that we left out the negative because we already said it's decreasing. So that's it for you.